Well, welcome to the third of my talks on world history. And this one will be primarily about the evidence for the flood from the perspective of geography as opposed to geology, which was my talk from last time. However, I do want to start, as it were, with the evidence from geology, because in my last talk, I hadn't quite mastered how to share, as it were, the PowerPoint whilst at the same time speaking. So I think I've mastered it this time, hopefully. We shall see. So I'm now going to share the PowerPoint that I should have shared last time. And hopefully this will work now. So I'm just going to share it. And as I said, this was a talk I did a couple of years ago on the irrefutable evidence for the worldwide flood. And I'll now, as it were, speak to this PowerPoint, and I will go over quickly the geological evidence, and then I will look at the evidence from geography and landscapes. And it's my contention that the actual evidence is quite powerful. So hopefully we will have a chance to see this. So the first piece of evidence was the evidence for polystrate fossils. This is fossils of things like tree trunks that go through many layers of rocks. So hopefully this time around you'll be able to see that. And as you remember, I said that this is not plausible for this to happen over many thousands or millions of years, as would be indicated if those rocks were laid down gradually. And I did mention that this evidence is quite common, and it often goes through coal seams, many coal seams, which are supposedly millions of years apart. Again, really quite strong evidence that the layers were laid down in one catastrophic event. If you remember, I also talked about the soft tissue, and you can see evidences of this which Mary Schweitzer found. And as I explained, this has been found in lots of different animals. And as I say, I have sent the PowerPoint to people so that you can look at that in more detail. I then talked about the concept of transcontinental rock layers, things like the Coconina sandstone, which can be found all over the western states of America. And that's not really conducive to something that happened as a localized flood or a localized catastrophe. It would suggest a worldwide catastrophe. I then explained that these sorts of features, like the Tapeats sandstone, which can be seen not only in the Grand Canyon but in North America, but also in Israel and North Africa, again indicating a worldwide deposition rather than a local one. And similarly with the red wall limestone, which is found in the Grand Canyon here, but is also found in England and the Himalayas. Again, that's halfway around the world. That suggests a worldwide catastrophe, not a local one. And then I mentioned about the lack of erosion between the rock layers, which are supposedly a million years apart, but yet there seem to be no sign of those millions of years. These flat lines that you see brilliantly illustrated in the Grand Canyon because of the different colored layers of rock. And when you get up close, it's the same picture. Flat lines, no sign of erosion. What I would have expected, if you remember I mentioned that there had been millions of years of patches of time, even thousands of years, there should be evidence of erosion, gullies, and things where water would have created an uneven surface. In fact, what we find is consistently flat surfaces, and that is a good evidence for all these things happening at once. I then mentioned about the rocks that were bent, and that really can't happen unless the rocks were soft and malleable, which means that they must have recently been laid down, not yet dried out from the flood, and therefore when those, as it were, movements in the earth happened, the rocks bent, they didn't crack. And again, I think that's quite clear evidence that these rocks were recently laid down and laid down in a catastrophic way. Now I'm coming to the issue which I said would be the main talk, which is topography, is a very posh term for landscapes. And I think it's quite obvious that one feature that looks really strange here is how flat the top of this mountain is. Likewise, not so obvious, but it's actually very common around the world, is what we call plains, flat areas of land. See it in Siberia, see it in large parts of North America and Northern Europe. Now, these features are actually quite surprising, and they're not what you'd expect if you have a landscape that is millions of years old. This one here just is weird. You know, what could have planed off the top of a mountain so flat? You can see it there and there. It makes sense if you visualize, as it were, all of this land covered in water, potentially to a great height above the landscape. And then if the oceans sink by, let's say, 1 kilometer in depth, that water would suddenly move off the earth into the oceans. And you would have a situation where the runoff of that water would come in 2 stages. The first stage would be sheet water flows. That is very fast, large quantities of water across a huge area moving in the same direction. And that would have the effect of planing off a surface flat. Now, once that surface has been planed flat, you have the second stage. And that stage is interesting. This is when there's now not so much water around and dry land is beginning to appear. And you begin to have a more channelized version of this drain off. And that's when you have your big canyon formations and your more complex landscape formations that we'll look at in a minute. But you've got, in a sense, to think about 2 types of water flow. One is the sheet water flow that creates plane surfaces and these big, wide expanses. Then you have your channelized water flow, which we'll look at later, which is your end stage of the water draining into the oceans and leaving behind dry land. Now, planation surfaces are quite unique because if you had a recent, as it were, worldwide flood, you would expect to see the surfaces still to be flat, and there would be boulders potentially on top of the surfaces that actually belong to rock layers that belong elsewhere, that are just being carried along by the waters. So that's kind of debris, if you might say. If you were to believe that these surfaces have been around for millions of years, you would have expected to see differential erosion rather than planation surfaces. You would expect the hard layers of rock, which are often coming in at an angle, to be raised above the soft layers of rock, which would erode more quickly. And you might expect to see sediment from the broken up hard layers sitting at the, as I say, the valley section of the soft layers. So this is the type of landscape you would expect over a long period of time. But what we actually see in our planation surfaces is something much more like this, which is much more consistent with a worldwide flood. Mentioned to you that the second stage, which is the channelized version, is something which we see where we see these sort of water gaps. Now, the curiosity about these water gaps is that the water tends to find itself going through very steep gorges or steep sort of valley areas, and not always the obvious place you'd expect. And so in this case, the water from this lake drains out from this red arrow rather than the more obvious place, this red arrow. That makes sense if you realize that what's going on here is that as the water drains off the land to the sea, it will find a weakness in, let's say, this ridge of mountains, and it will dig into that. And what you may not realize is that water is an extraordinarily powerful agent when it comes to erosion. And if you have vast amounts of water, it will cut through very solid pieces of rock. But even though I'm saying that, you've got to remember these rocks, having been laid down in the flood, will not necessarily be the same strength as they are now, because they would still be probably quite damp and therefore quite easy to be eroded. So you have got many reasons why you have what sometimes look very complicated features. Take the Rhine Gorge. That is a strange feature that goes straight through a set of hills as the Rhine goes from the Alps down to the Dutch coastline. Or you might see the Iron Bridge Gorge in Shropshire. which again is the River Severn punching its way through a set of hills. And this is a common feature where, strangely, rivers go through whole hills or mountains as if they don't exist. But of course, if you're thinking about it, if the water has been running off, it's not so illogical. And you must remember that by and large, the rivers in this country and around the world do not create the valleys that they follow. They actually follow the valleys that were created by a catastrophic agent. So it's quite a different way of looking at things. Rivers follow valleys, they don't create them. Rivers are far too small to create the big valleys that they find themselves in. Another interesting, what we call topographical feature are features where you have cliff faces. They're called erosional remnants. Now, this is famous, Devil's Tower. Any of you ever watched Close Encounters of a Third Kind will remember this one. This is a Steven Spielberg film from the late 1970s. I remember seeing it. Now, the feature here, which looks really intriguing, is this cliff face. How did that cliff face survive millions of years? You know, exposed rock is a very fragile environment. And as we do teach in year 8, you will find that the exposed rock will disintegrate for at least 2 reasons. One is freeze thaw, where water gets in and it gets broken up by the action of freezing. And then the other one is onion skin, where the heat in the day followed by the cold at night expands and contracts the rock, and it literally flakes away. So rock surfaces like this, vertical rock surfaces, do not last very long. And so it's really strange to argue that this is millions of years old. Much more likely that this is a remnant. All the material around it was washed away in that sheet flow of water. This, because it's maybe of a stronger nature than the surrounding material, is left exposed and has been exposed for a few thousand years, no more. And that's interesting, because one proof of that's the case is if you look at the base of these places, there's very little what's called talus, that is erosional material at the base, which is what you'd expect if these are only thousands of years old, but not what you expect if this is millions of years old. You expect lots of broken up rock at the base. And this is a sort of explanation of what would have happened if you had believed that this was millions of years old. Really, it would have eroded to nothing. But if you believe that this is actually only thousands of years old, and what happened was that the sheet flow of water took it away, then that you will see is quite an easily explained geographical feature. This is another one from my local area, which is the South Downs. Again, you could see what was once in the North and South Downs a continuation of chalk that would have possibly gone up to 1,000 meters in height. And it's not difficult to see what the shape would have looked like. It would look like this. And all of a sudden, it gets washed away by that sheet flow that I was describing. And that leaves this feature. You will see here that in the Grand Canyon sits here. Now, the Grand Canyon is obviously an erosional feature that took place towards the end of the flood, but all these other big, flat, planed areas would have been from the sheet flow going into the Pacific. When I went on my trip to the Grand Canyon, I came to what's called the Vermilion Cliffs, and the Grand Canyon, as you can't see, is like a gorge that's going to come all the way around there here. But this is a sort of plain here, and this is the Vermilion Cliffs. And if you get up closer to the Vermilion Cliffs, I don't actually see it there, you'll see that there is very little at the base of these cliffs of any erosional material, suggesting that these cliffs can only been around for a few thousand years. There are a number of other features that I explain in addendum 7, which is page 77 and 78. I won't go into them now, but just to say that what I've just described here is just one of a number of what we call landscapes that make sense from a worldwide flood perspective and the erosion from the sheet flow of water, but doesn't really make sense in terms of a long age. I'll look at biology in my next talk, not this one, because that's a subject in its own right. And I'll look at history later on when I come to deal with the history of the world post the flood. But it is interesting to notice what evidence is there. Now, before finishing this talk, I think it's really important to consider what is the evidence for an old Earth and how does that stack up? Now, I can't say I'm an absolute authority on this. I did try to look it up, and the three evidences that I spotted was radiometric dating, which I did allude to in my last talk, what was called index fossils, and then time to form the rocks or time to form landscape features such as canyons, etc., and mountains. I think that the thing about index fossils I will not discuss in any detail because that is based on the idea that evolution is true. And I think the soft tissue in fossils indicates where I'm coming from there. And my talk next time will talk about that in more detail. So I'll just consider the two other issues, which is radiometric dating and time to form rocks. The issue here is that radiometric dating is based on a number of assumptions, and it may not actually be measuring time at all. It's certainly measuring something, and I would say it's the strongest of the arguments against a young, recently formed landscape, because there's definitely results coming out that do suggest a very old age. But there are also issues with radiometric dating. So if we kind of look at the geology of the Grand Canyon, there is this large lava flow that comes down the sides of the Grand Canyon. Now, if you're taking standard geology, this would be to the tapetes down here, for instance, which we looked at earlier. That should be around about 500 million years old. And going up to Kaibab, which I think is about 150 million years old. So you've got here what looks like hundreds of millions of years worth of rocks. Okay, this, by the standard interpretation, lava flow is reckoned to be about 6 million years old. Yeah. And that we'll come back to that in a minute. But there are definitely inconsistencies in the dates that you get from various rock formations. So you get a situation which is called the Cardenas basalt, which I'll go back to. Cardenas basalt is here, this Cardenas basalt, that does emerge at some points in the Grand Canyon. And the dates you have variously for that are using the krypton-argon method. You have 516 million years. The rubian strontium method, it's 1,000 million years. And also, got a little excited about that one. Let's go back. Yeah. I can't now remember what that last one is, but I'm sure it's quite an exciting set of elements. That one is 1,500 million years. So it's clear they don't all agree with each other, which is a bit disturbing. But then we come to this rather interesting feature here. This interesting feature here is the remnant of that lava flow that I was talking about, which, you know, generally speaking, is considered quite recent and has, as you can see, covered all these other layers of rocks. So it's pretty obvious that must have happened since those rocks were laid down. Yet, when we look at the dating for that, it is given a date of over 1,000 million years. In fact, if you look carefully, this rubidium strontium one is 1,000 million years for that lava flow. And yet the Cardenas one, if you remember, was only 1,000 million years. So it appears to be a little bit inconsistent to say this is actually older than this. And I think it's that level of, as it were, errors, or let's say inconsistencies or anomalies, that make people think that maybe this system is not quite as reliable as we believe. Furthermore, there are things like coal, which is supposed to be 60 million years old, which has carbon-14, and diamonds, that's 1 billion years old, has carbon-14. And we know that carbon-14 only has a life of about 50,000 to 100,000 years at max. And this is consistent, obviously, if you remember, I mentioned last time about the fossils having carbon-14. So I think we have real evidence here that whatever's going on, it's not unreasonable to suggest that, in a sense, we're not measuring time, we're measuring something else. Now, I'm going to pass by the biological side, thing about index fossils and look at the concept of gradual rock formations. So up until the explosion of Mount St. Helens in 1980, there was, well, you might say, a reasonable assumption that things like canyons, like the Grand Canyon, must have taken a long time to form. Certainly, if you're thinking about the river forming the canyon, it would seem a reasonable thing to believe. But what we discovered was that when you have a huge catastrophe or a huge event like a volcano erupting, in the case of Mount St. Helens, a very explosive volcano erupting, things that you think would take a long time happen very quickly. So we found that rock layers, this sort of stratified rock layers, can take place in a matter of an hour. So it didn't happen that these were laid down annually. These rock layers were formed as the explosion and all the associated slurry and dust and particles sorted themselves out into layers as they settled. And so we don't have evidence here for a long period of time. We have evidence here just for a catastrophic event. Likewise, we have here this canyon system, which we can see, which is like a miniature Grand Canyon, 1/40th scale, with the same complex system of side canyons. Now, this was formed in one day. We know that because we have evidence of what it looked like before the mud flow broke and all the water gushed out in 1982. And we have evidence of what it looks like now. So it took one day for this to form, not many years, even just a one-off catastrophic event. This is an interesting situation. This was solid rock, old pre-volcanic rock, as it were. This canyon system did not exist before the eruption in 1980. Something happened in 1980 during the volcanic eruption that created a canyon. Now, you could, if you came to this canyon, think this river formed the canyon, one grain at a time. But in fact, we have evidence that this canyon didn't exist, and effectively the next day it did. And the river, being what water does, it flows down the lowest possible course. Again, confirming the suspicion that rivers follow valleys, they don't create them. In a sense, it is the catastrophe that creates the valley, not the river. And this is an interesting one, but I won't go into it because this is about how you can have what looks like a series of fossilized forests, but they can actually just be logs that came washing down from a catastrophe. Most rock formations require energy, not time. And I have a sneaking suspicion, and I write about this in pages 10 to 15 of my world history book, that a lot of what we call everyday geography features really do betray a recent Earth. And you will find this particularly in things like estuaries. River estuaries silt up. They don't get created except by catastrophes. And the estuaries, I would suggest all of them around the world, would show that they have only been around for thousands of years. Because without the use of man-made dredging, by and large, estuaries silt up and become pretty useless from a navigational point of view. And likewise, I think we would find that gorges, with their backward erosion creating short backward erosion of waterfalls that create gorges. The size of the gorges, I suspect, almost always would portray a recent formation. In other words, if you were to take the gorge and work out how much erosion has taken place every year, you would come to thousands of years as being the maximum length of time for those gorges. And I have a feeling that if you were to go around and look at a lot of features in the world and ask yourself the question, how many thousands of years would erosion, how many thousands of years of deposition has been going on here? Because I think the idea of 1 million years of erosion and 1 million years of deposition, if you really think about it, is not realistic. Take, for instance, the Holderness coastline. The Holderness coastline erodes at around about 1 to 4 meters a year. Now it's on the east coast of Yorkshire. 1 million years of such erosion would actually take the coastline back 1,000 kilometers. Now, that's not realistic because 1,000 kilometers would take out Yorkshire, Lancashire, and everything else. And I realize that some would argue, well, there's the Ice Age and things like that. And I think that's fair dues. But I have a feeling if you were to use the concept of 1 million years of erosion to most features that we see in geography, or 1 million years of deposition, just that simple question, what would that do to this particular feature? I think you might come up with a quite surprising answer that would say, that's not realistic. And therefore, I think the idea that the landscape is only thousands of years old, laid down essentially by a worldwide flood, with some alterations with a ice age that took place afterwards, and the tectonic processes that would have been attendant on the first 500 to 600 years after the flood, where volcanoes and earthquakes might have been quite common and quite powerful. Once you factor all those things in, I think you probably can reliably say that the landscape does look like a recent landscape, and a landscape that has only suffered thousands of years of erosion and deposition. And so that's what I would call the arguments from geography. And my next talk, I will look at the issues around biology and evolution. Thank you for listening.